Anand. Hi everyone. Hi everyone. Dr. Munal Kare, respected head, Shah sir, our guests, Dr. Devsar, all the faculties, and all my beloved students. I welcome you all for today's online workshop on NMR and ESR Spectroscopy. Spectroscopy is important in every field, as it helps us to characterize the sample, its structure, bonding, and composition. To know more about this workshop will help us to enhance our knowledge. Now, I request Dr. MC Kare, sir, Principal, Anand Niketan College, Warora, to say a few words.
हॅलो, सर्वांना नमस्कार. श्रद्धेय बाबा व ताई, महारोगी सेवा समितीचे संस्थापक सचिव यांना विनम्र अभिवादन करतो आणि आजच्या आयोजकांचे आणि वक्त्यांचे सर्वप्रथम अभिनंदन करतो की फार चांगला टॉपिक त्यांनी जो युनिव्हर्सल ऍप्लिकेशनचा आहे असा वर्कशॉपसाठी निवडला. आजच्या या वर्कशॉपला आपल्याला लाभलेले आदरणीय देवसरकर सर आणि टेकाळे सर हे फार अनुभवी व्यक्तिमत्व आहेत दोघे. आणि त्यांच्या अनुभवाचा आणि त्यांच्या ज्ञानाचा या वर्कशॉपला आपल्याला जरूर फायदा होईल. सर्व विद्यार्थ्यांनी त्याचा पुरेपूर फायदा करून घ्यावा. आणि हे दोन्ही टॉपिक्स असे इतके महत्वाचे आहे की तुमची नेटची परीक्षा असो किंवा तुम्ही जेव्हा PhD साठी रजिस्ट्रेशन करता त्याच्यानंतर जे काम करता या सर्व बेसिक रिसर्च मध्ये स्पेक्ट्रोस्कोपीचा फार मोठा उपयोग प्रत्येकाला होतो. लाईफ सायन्सेसच्याही पोरांना होतो आणि केमिकल आणि फिजिकल सायन्सेसच्याही पोरांना. आरोग्य सेवा समितीचे हा वर्कशॉप सगळ्यांसाठी फार चांगला राहील. ज्ञानाच्या अशी अशा बाळवडिलांचे या वर्कशॉपसाठी सर्वांना शुभेच्छा देतो. जय हिंद. ऍप्लिकेशनचा आहे असा वर्कशॉपसाठी आपल्याला लागलेले आदरणीय देवसरकर सर आणि टेकाळे सर हे व्यक्तिमत्व आहे दोघे आणि त्यांच्या अनुभवाचा.
Hello, good morning to all of you. I welcome all the respected participants and
तुमची नेटची परीक्षा
Dr. Sir and Dekade Sir. I welcome all of you. I am not and that workshop will help all of you because spectroscopy is very important topic. I am not wasting the time. I am very thankful to all my team. Okay, thank you all of you and welcome all the participants in this workshop.
Thank you, sir. Now it's time to introduce our guest speakers for today. The guest speakers for today are the first speaker is Dr. Santosh Devsarkar sir, Associate Professor, Swami Ramanand Tirth, Marathwada University, Nanded.
I welcome all the
His topics of interest are thermodynamics, chemical kinetics, electrochemistry, quantum chemistry, spectroscopy, research and research. He has total 12 years of research experience. He has published 55 research papers and he has 5 research papers published in conference proceedings. Under him, 5 students have been awarded for PhD and 4 students are holders. He has also guided students for MP and 52 students for MSc dissertation. Now I would like to introduce our next speaker for today, that is Dr. Pradeep Dekade sir, Associate Professor and Head of Department of Chemistry, Shiksha Mandal, Bajaj College of Science, Warora. He has done a PhD, NET, ZET and REC, and his area of specialization is organic chemistry. He has completed, he has published 14 books, out of which 7 are international and 5 are national. He has total 12 years of research. He has guided 30 students for PhD dissertation, and he has 5 research papers published in conference proceedings. Under him, 5 is all about water. Now I would like to request Dr. Devsarkar sir to present his topic for today. And he is going to speak on ESR Spectrum. Our next speaker for today is Pradeep Dekade sir, Associate Professor and Head of Department of Chemistry.
Shall I start?
Science. Yes sir, you can present your screen now and you can start.
So first of all, I am very much thankful to the principal of this college, Professor Dr. Kale sir, respected management of the institute, and my friend Shaukat, as well as all the coordinators and all the teachers involved for the organization of this particular event. So thank you for inviting me for such an interesting topic to deliver the talk on this topic. Now let me share the screen. Please, Dr. Ashish sir, the screen is visible or not?
Visible, sir. Visible, sir.
Screen is visible to you?
Yes, sir. It is visible.
But it is not showing to me. Just give. Sir, it is visible now?
Sir, it is visible.
Okay. So, shall I proceed?
Yes, sir.
Friends, as you know that the physical methods of analysis, the physical techniques of analysis and chemical method of analysis are available for the different chemical compounds which are useful particularly in the pharmaceutical and medicinal sciences. One of the important technique for characterization and qualitative and quantitative analysis of the compounds is a spectroscopic method, which is a physical method of analysis. And as you know that there are again number of different techniques in the spectroscopy depending upon the interaction of the way of interaction of radiation with the matter as well as the frequency or energy of the electromagnetic radiation. Two of such important techniques are available in the spectroscopy, which are nuclear magnetic resonance spectroscopy and electron spin resonance spectroscopy. Both the spectroscopic techniques are spin resonance spectroscopies. As we know that in nuclear magnetic resonance spectroscopy, as the name indicates, the nuclear spin undergo transition or resonance, whereas in electron spin resonance spectroscopy, the spin of electron which undergo transition or resonance. So basically these two techniques are very similar. Both are the resonance, and I am fortunate enough to present one of this resonance spectroscopy before you, and also my friend Professor Dr. Pradeep Tekale sir will be presenting the nuclear magnetic resonance spectroscopy. So I will be fortunate to attend his lecture also. So this is a resonance spectroscopy where the electron spin is involved. In the nuclear magnetic resonance, nuclear spin is involved. Depending upon the magnetic moment of the nuclear spin and electron spin, there will be the differences in these two spectroscopic techniques. This is a short outline of the lecture. I would try to cover these things during this lecture. Introduction, principle and theory, experimental setup. Yes, hello. Am I audible?
Slideshow is not running. Slideshow.
Slideshow. Yes, sir.
The slide is not completely visible. It is not in a slideshow mode. Please switch on the slideshow mode.
Okay. Just give me a second.
Okay, sir.
So it is okay, sir? Hello? Hello? Hello?
Please.
Yes. Yes, sir.
Click on the option which is on the left side of 66% on your screen.
Top.
No, sir. At bottom right side, that is showing 66%. It will show full screen.
Full screen, yes, sir. Okay. Full screen. I have clicked the full screen now. Yes, sir. Hello.
Wait a minute, sir.
Full screen. Yes.
Sir, I'll just tell you, we'll be presenting my screen now. So you can see how to maximize the screen.
Okay.
Just a second. Like I'm going to this presentation. So you can see this slideshow, right? On which I have clicked now. If I do this, then it will come the full screen, and the students can see your whole presentation.
Okay, I will first this now from beginning. I am stop. I have stopped presenting now. Okay.
Okay.
Now present now.
Okay. See, I have selected my screen, and now I'll be sharing this. Okay. Now I have gone to presentation. Right. My PPT is visible. Right.
Okay.
Yeah. So now if I go on this slideshow, you can see this arrow.
1 minute. Where, madam? Okay.
Yeah. So if I click on this, the presentation will be like full screen.
Yes, ma'am.
Yeah. Now you can share your screen, sir.
Yes. So while sharing, present now, and then a window, right?
Yeah. Yes. Go to your presentation window, and then you can go to slideshow.
The PowerPoint presentation which is open there. So share. Sharing.
Yeah. Yes. Now you can see this slideshow that is left to that 66%, right? You can see it there.
That particular is not shown here. That is.
Yes, it is there, sir. यहाँ नीचे अगर आप देखेंगे ना right side में जहाँ पे आप zoom in, zoom out कर सकते हो वहाँ 66% लिखा है. नहीं तो सर आप F5 प्रेस कीजिए आपके लैपटॉप पे.
Okay.
F5.
F5. Yes. F. No, it is not. But
Okay. No problem, sir.
I will again stop and then try. I will try again.
Okay, try again.
I like share your entire screen or a window.
Entire screen करो sir.
Entire screen. Okay. Entire screen में
entire screen
PPT नहीं दिख रहा है.
क्या नहीं दिख रहा है सर?
PPT नहीं दिख रहा है मेरा. ओपन है. Entire screen में.
उस विंडो को क्लिक करो सर. वहां पे एक विंडो आएगा, उसको क्लिक करो और फिर शेयर करना. अब आप आपके पीपीटी पे जाइए.
PPT.
एग्जैक्टली. वेरी गुड.
अभी दिख रहा है?
दिख रहा है सर. अब आप कंटिन्यू कर सकते हैं.
तो मुझे सिर्फ PPT दिख रहा है, बाकी कुछ नहीं दिख रहा है इधर. बराबर है ना?
कोई बात नहीं. हमको आपकी आवाज भी सुनाई आ रही है और आपकी पूरी स्क्रीन भी दिख रही है.
इधर साइड में मेरे को ऐसा ये नहीं आता क्या? आप बाकी लोगों का ऐसा या मेरा वीडियो ऐसा नहीं दिखता ना?
सर आपने अभी वीडियो बंद करके रखा है इसलिए नहीं दिख रहा है.
ओके. तो मैं
आप वीडियो ऑन कर सकते हो आपका.
वीडियो ऑन है.
वीडियो पे बराबर. अब आ रहा है सर.
अभी आपको आ रहा है क्या?
आ रहा है सर.
कंटिन्यू करूं मैडम?
कंटिन्यू कीजिए सर.
ठीक है. So these are the points that will be covered in this lecture: introduction, principle and theory, experimental setup, hyperfine splitting, and applications of the ESR technique will be covered through the different examples. Friends, this particular technique for the study of paramagnetic substances was developed by a Soviet physicist, Evgeny Zhavisky in 1944, and independently it was developed at the same time by Brevis Blenny at University of Oxford. This particular technique is accepted for it is a non-destructive technique and can be performed with the sample in all the three phases, gas, liquid or solid. It has a lot of applications in pharmaceutical and agriculture basic research. This particular technique is also useful for the applications like production of lines in semiconductors and coatings, and also in clinical and medical fields such as cancer diagnosis. This particular slide I have shown at the beginning in order to increase the interest of the listeners and the readers particularly in this technique, so that they can also understand the applications of this technique. This technique is useful for studying particularly the paramagnetic substances containing unpaired electron. So therefore, free radicals, any type of free radicals can be studied by this technique. Transition metal compounds or transition metal complexes with paramagnetic nature, that is containing unpaired electron, can be studied by this technique. And during the electrochemical oxidation and reduction, as we know that different type of species are generated, so those species can also be studied by using this ESR or EPR, electron spin resonance or electron paramagnetic resonance spectroscopy. As I told you earlier, the basic concept of NMR and ESR are analogous, but the electron spins are excited instead of nuclear spin. In case of the ESR, electron spin is excited from one energy level to the another energy level in presence of external magnetic field. And in nuclear magnetic resonance spectroscopy, the nuclear spins are excited. So, coming to the basic principle and theory of this particular technique. Dear friends, what happened? As you know that the electron has a spin, that is plus half and minus half. So therefore, it would have a magnetic moment. It will produce a small magnetic field and it would have a magnetic moment. In the absence of magnetic field, the two spin states of the electron, unpaired electron, a single electron, that is plus half and minus half, are degenerate. The energy levels of that electron are degenerate. But the moment we apply the magnetic field, external magnetic field of particular strength to that unpaired electron or the substance containing unpaired electron, then the two spin states of the electron aligns. One aligns anti-parallel to the external magnetic field and another aligns parallel, and there is a splitting of the otherwise degenerate energy levels of the electron in presence of external magnetic field. This is a normal Zeeman splitting, the one which occurs also in case of the nuclear spins. Nuclear spin also gets split in presence of the external magnetic field. So as shown here in the absence of external magnetic field, there is no splitting of the spin states to spin state of the electron. But the moment we apply the different external magnetic field, that is B, then there is a splitting of the two spin state, splitting into two energy levels. And this particular splitting, as can be seen from this diagram, is directly proportional to the external magnetic field strength. As we increase the external magnetic field strength, the gap between these two spin states will increase. And this splitting of the two spin states of the electron forms the basis of the electron spin magnetic resonance spectroscopy. Once, as you know that, once the energy levels are formed, then by supplying the electromagnetic radiation of corresponding energy, one can promote or one can have a transition of that particular spin, maybe electron spin or nuclear spin, from lower energy level to the higher or vice versa. So this can be done. And when a electromagnetic particular wavelength or frequency is supplied at constant external magnetic field, then either absorption or emission spectrum is observed in this case. That is, the lower spin state may get transition to the higher energy level or vice versa. So when lower spin state undergo transition to higher one, we will get the absorption spectrum. The electromagnetic radiation of particular frequency will be absorbed. And during the transition of higher spin state to the lower spin state, particular electromagnetic radiation of particular frequency will occur. So therefore, emission or absorption spectrum is observed. Generally, according to the Boltzmann distribution, as we know that the population of the spin states of electron or the nuclei in the lower energy level at room temperature it exceeds the population in the higher energy states. When the ratio of this population of spin state in higher to the lower energy level is calculated, it is always less than 1, indicating that there are some more number of nuclear spin states available in the lower energy level as compared to the higher energy level. So therefore, generally it is the absorption spectrum, because there are some few more number of nuclei are available in the lower energy level. So therefore, moment we supply the external electromagnetic radiation of particular frequency at constant magnetic field, the nuclear spin states from the lower energy level start absorbing the electromagnetic radiation of particular energy, and they will get excited to the higher spin state. So a particular then absorption peak will be observed, which is shown over here. Am I audible to all of you? Sir? Ashish sir?
Yes, sir, you are audible.
Yeah, okay. So absorption, like this absorption peak is observed. So this is the absorption peak, and this is a BZ, is a magnetic field. Now this is a somewhat broad peak, and therefore to have a correct value of the magnetic field at which the absorption has take place, we take the first derivative of that peak. So you can see here now the correct or more appropriate, more correct value of the external magnetic field can be obtained. So in this way, when a paramagnetic substance containing one unpaired electron, it is exposed to the external magnetic field of particular strength, and the electromagnetic radiation of particular frequency is incident on it, the absorption of light, that is electromagnetic radiation, take place, and we get the absorption signal, of which first derivative we take to calculate the correct value of the magnetic field. The external magnetic field that we can apply practically in the laboratory. So for that particular magnetic field, the corresponding electromagnetic radiation required for the transition of spin state of electron from one energy level to the another, that belongs to the microwave region of the electromagnetic radiation, Whereas, as you know that in case of the nuclear magnetic spectroscopy, electromagnetic radiation belongs to the radio waves of electromagnetic radiation. As I told you at the very beginning, the NMR and ESR both are the resonance spectroscopy. So therefore, there will be the only differences because of the spin magnetic moment or the magnetic moment of the electron spin and nucleus spin. So whatever the differences between NMR and ESR will be there, so this will be only because of this thing, that is a magnetic moment, strength of the magnetic moment of electron and the nucleus. So here also, as I have mentioned, the microwave region and radio wave region. Then if you see, the frequency of microwave region is more than the frequency of radio waves. It clearly indicates that the electron is more stronger than the magnetic moment of the nucleus, and therefore it requires slower energy or the frequency for transition of the electron spin states from one energy level to the another energy level. You can also see, Ashish sir, the screen is visible, no?
Yes, sir. It is visible.
Okay.
It is visible.
So I will proceed. Okay. So
Yes, sir.
yes. So we can also see here I have written a equation for this particular transition. That is a common energy difference between the lower and higher energy level. That delta E changes with the external magnetic field. This I told you earlier also. This changes with the external magnetic field B. You can see this is increasing as the external magnetic field strength is increasing. So this particular delta E at for a given constant value of is equal to G mu into B. So there are three things: G, mu, and B. So B we understood. Delta is directly proportional to capital B. That is the external magnetic field. As the strength of external magnetic field increases, the gap between two splitted spin states energy levels of the electron also increases. Agree. There are two more things which also are connected with or related with this particular gap, energy gap, that is G and mu. This particular G is a Electron G factor. It's an Electron G factor, and it is a dimensionless factor, and its value as shown below in that slide is 2.0023 for free electron. And friends, it gives you the position of the signal in the ESR spectrum. It will give you position of signal in ESR signal. How this value is calculated? G is equals to h nu divided by mu into capital B. So by accurately measuring the magnetic moment applied externally, frequency of which is absorbed during the resonance process, at the resonance it is constant, and mu will give you the information about the magnetic moment of the electron, which is produced because of its spin or angular motion. As you know that this particular electron having spin plus half or minus half, it has magnetic moment, and that magnetic moment has came from two different type of motions of the electron. One is a spin motion of electron where it rotates around its own axis, and another one is the orbital motion of the electron around where it rotates around the nucleus of the atom. So therefore, spin motion and angular motion of the electron contributes for the this magnetic moment of the electron, and this particular mu is so it gives you that magnetic moment of the electron. So in this way, this single slide, dear friends, this single slide explains you the principle of this particular principle and the basis for this particular ESR technique. I repeat in 2-3 lines. A paramagnetic substance containing unpaired electron, when it is placed in external magnetic field, then the otherwise degenerate energy levels of this electron will get split into two lines, plus half and minus half, and then a transition of the electron spin from lower energy level to the higher energy level can be carried out by the absorption of electromagnetic radiation, and we will get the absorption signal. To calculate the accurate value of externally applied magnetic field, we take the first derivative of that absorption signal, so which will look like this. And The equation for this absorption or resonance is delta E is equals to G mu capital B is equal to H nu. H nu is the frequency or energy of the electromagnetic radiation, that is microwave radiation absorbed for the transition of spin state of electron from one energy level to another energy level. Mu is a magnetic movement of electron, which is because of the spin and orbital motion. G is a electron's G factor, which give you the exact position of the signal in the ESR spectroscopy. Some 2-3 important things maybe already maybe covered in our discussion have to be taken into account while studying in the ESR spectroscopy. For the limitations in the in the laboratory, the corresponding electromagnetic radiation for observing one. Now there are two options for observing the resonance. One can have a static magnetic field or static electro region, that is the frequency of electromagnetic radiation. This particular graph obtained is absorption versus magnetic field. So this we are, as for example, I have quoted here from some book, that is for magnetic field of 3400 Gauss, above 9 to 10 gigahertz microwave frequency is required, which belongs to wavelength 3.4 centimeter. So you know, and you can compare this particular data in this example with that of the NMR. You can see that this particular 9 to 10 gigahertz of the frequency belongs to the microwave region of the electromagnetic radiation, and of course this is greater than the frequency required for the flipping of the spin state of the nucleus, nuclear spin state flipping. So I have mentioned this also here. As you know that in NMR spectroscopy, TMS is used as a internal standard for comparing, the intensity as well as the position of the absorption energy absorption. So here also in ESR spectroscopy, DPPH, that is 2,2-diphenyl 1-picyl hydrazine, is used as a standard for two important things. Number one is the position of the signal and intensity of the signal. Position and intensity of the signal. And we'll come to know that directly. I have shown here this particular compound shows 5 lines in its ESR spectra. We'll come to this later on once you understand how these lines comes. This is an experimental setup required for the ESR spectroscopy. We will not discuss much about this, but 2-3 important things are required. As I told you, one is magnets are required, magnetic field for splitting of the electron spin states. Then electromagnetic radiation is required, klystron, that is a source of micro radiation. Sample holder is required, and this will modulate modulation, and then detectors are required for measuring the absorption frequency or the magnetic field, and then other computer software devices are there. So particularly the magnetic field is required. This microwave frequency sample holder, and so by keeping one of these two constant, other can be varied, and the absorption is studied. So these are the different parts: micro radiation source, then sample cell, magnetic field and sweeping circuit for changing the magnetic field, detection system, data acquisition, and computer control. So these are the different parts of this particular technique. I have a small problem, madam. Hello.
Yes, sir.
When I am sharing the full screen of my PPT. Hello.
That's right, sir.
मी जेव्हा फुल स्क्रीन शेअर करतो तेव्हा ते बाकीचं मला हे साईडला काही दिसत नाही आहे, म्हणजे
नाही सर, नाही दिसणार ते ऑप्शन
पार्टिसिपंट्स किंवा इव्हन मी पण दिसत नाही. जसं झूम मध्ये आपल्याला साईडला आपण स्वतः दिसतो ना.
सर याच्यामध्ये फुल स्क्रीन शेअर करतोय सर आपण, त्याच्यामुळे ते पॉसिबल नाही होणार याच्यामध्ये.
ठीक आहे, म्हणजे ठीक आहे. मला असं वाटत आहे की कधी कधी तुम्हाला आवाज येतो किंवा
नाही येतोय सर.
आहे ना?
हो सर.
मला फक्त असं वाटत आहे की मी स्वतःशी फक्त एक स्क्रीन दिसत आहे माझा, मला काही दिसत नाही
सर. बाकी सगळेजण
ओके ना?
हो सर.
ओके. तर काही अडचण असेल तर यू कॅन जस्ट टेल मी. ओके.
हा सर.
दिस इज ओके सर नाउ? स्क्रीन इज ओके.
इट इज विजिबल.
Okay. Now, the second important part of this particular technique is a hyperfine splitting. Hyperfine splitting. This we can compare with the splitting of the signals. That is a proton. For example, in 1H NMR proton signal into some n+1 lines because of the other nuclei present nearby having the non-zero spin. So, in the same way, this particular electron, as I told you, this is a spectroscopy of paramagnetic substances containing at least one unpaired electron. Now, till now we have studied there is a splitting of the electron spin state into two, plus half and minus half. One external magnetic field, another one is opposing. And among that two states, the transition can be studied through the absorption of microwave radiation of particular frequency, and we get the absorption signal, first derivative, you know that. Now what happened, friends, if this particular electron is not a single free electron and some magnetic moment having environment is there around this particular electron, then the splitting like NMR splitting occurs here also, and that is but natural, because this particular person electron with its spin plus with its spin, two spin states plus half minus half splitted, it is having the magnetic moment because of spin and angular momentum, spin and orbital angular momentum. So therefore this is some active species magnetically, and definitely it will interact with any magnetically active nuclei maybe, or a species that is present nearby to this particular electron, and such thing happens. Friends, if any nuclei having non-zero spin, that is, it is not having zero spin, non-zero spin, but it may be half spin, 3/2, 5/2 spin, or 1, 2, 3, 4 like this spin, our electron magnetic moment interacts with the spin of that nucleus, and because of that interaction, each of the splitted spin state of the electron, each of the two splitted spin state of the electron get further splits into 2n+1 line. Particular phenomenon is called as the hyperfine splitting. Hyperfine splitting. First, it is called as HFS, hyperfine splitting, and the splitting, the one which we have already studied, that is a simple splitting of the electronic spin state. This is a hyperfine splitting, is the splitting of, so how will you define now? It will be the splitting of the two spin states of the electron, which have been already splitted in the presence of splitting of the two spin states of the electron into some 2n+1 lines, where n is the number of nuclei having spin I, capital I. So that is called as the hyperfine splitting. So we have to remember this particular formula, 2n+1, where n is the number of nearby that nucleus, that electron, unpaired electron, or should interact with that electron, that nuclei. So that distance should be such that it should interact. I is the spin of nucleus. For example, our 1H hydrogen, it has a spin half. Deuterium has spin 1. Nitrogen has 7 nitrogen 14 has spin 1. So that spin. that is a spin of nucleus, and spin of electron. So we should remember this. So spin of electron is interacting with the spin of electron, is interacting with the spin of nucleus, and some types of splitting has been taking place, which is called as the hyperfine splitting. And this splitting is very specific and splits each of the line of the electron spin state into 2ni+1 lines. For example, if it is a hydrogen atom, we'll just consider hydrogen atom. Then for hydrogen atom, now just I would like to ask any one of the MSc student, if it is available, he or she can unmute and tell me now, for hydrogen atom H, there is a one unpaired electron, right? And one hydrogen nucleus, which has been half. I told you formula 2ni+1. If you have a pen and page, please put the value of n. N is the number of nuclei having spin, non-zero spin. I is the spin put, and tell me how many lines into how the spin state of nucleus electron will get splitted. Please, any MSc student. Anyone can tell me? Ashish sir, I am audible?
Yes, sir, audible.
Okay. So please tell any student to give the answer of this question. Hundred participants have joined this particular meeting. Anyone? Okay. No problem. So it is just N is the number of nuclei. As I told you, it is a hydrogen atom. So only one nucleus is present, that is H, hydrogen, proton. So here it will be 1. 2 into 1. And I is the spin of that particular nucleus. It should not be 0. And yes, it is not 0. For hydrogen, it is half. So therefore, 2 into 1 into half plus 1 is equals to, so 2 will get cancelled, we'll get the answer 2. So in how many lines? The splitting will occur? 2 lines. That is basically 2 splitted spin state of the electron. 2. Now this will get split into 2. This will get split into 2, and this will get split into 2. Like this will occur. Each of the splitted spin state of the electron get further split into 2 lines for the hydrogen atom. So that's what I would like to tell you. Now, when that lines are splitted, then again for the resonance to occur or the absorption to occur or transitions to occur, there are certain selection rules. 2 important selection rules of the ESR spectroscopy. One is for the transition of spin state of electron, which are splitted by Zeeman splitting. It is delta ms is equal to plus minus 1. Delta ms, that is for electronic spin state. So here I will go back now. Here the selection rule is delta ms is equals to plus minus 1. That is transition of spin state of electron from this place to this place can occur, or this place to this place can occur, because both of these transition, that is absorption or emission, follows perfectly that rule, that is delta ms is equals to plus minus 1. Now, after interaction with the magnetic moment of the non-zero spin having nuclei, the lines have been split into 2 Ni+1 lines. So therefore, the selection rule for transition among that hyperfine splitted lines is delta Mi is equal to plus minus 0. Only those lines or transitions are allowed for which delta Mi, I for nucleus now, and S for spin of electron. So that particular terminology we can understand. So delta Mi is equals to plus minus 0. So please remember these two selection rules for further understanding. Now, once the lines are splitted, then by absorption of the electromagnetic radiation from microwave region, the transitions can be studied. And when we get the signals, for example, in case of the hydrogen, we will also see later on, the doublet is observed. 2 lines are observed. As I told you, when you solve this equation, you get 2. We already solved 2 lines. And the distance between that 2 lines, that is called as a hyperfine splitting, hyperfine coupling constant. That is a spacing or distance between the two successive lines in the ESR spectroscopy, and it is measured in Tesla or millitesla. As we have a coupling constant in NMR spectroscopy, this can be compared with the same coupling constant in our ESR spectroscopy. This is called as a hyperfine splitting, hyperfine coupling constant. So this particular slide significantly reflects 2-3 important things that we have to remember. That is, number 1 is the interaction of magnetic moment of electron with that of the magnetic moment of the non-zero spin having nuclei, nearby nuclei. And that interaction splits the 2 spin states, both the spin states of the electron into 2 Ni+1 lines. Number 1. Number 2 is after splitting, there will be the absorption of electromagnetic radiation and we get the number of lines. And for the transition between that number of energy levels, the selection rules are delta Ms is equal to plus minus 1 for electron spin energy levels, and delta Mi is equal to 0. Delta Mi is equal to 0 for hyperfine splitted lines. And number 3, the spacing or distance between 2 successive lines, signals in the absorption signals in the ESR spectroscopy is called as the hyperfine coupling constant. So these 3 things we should remember: 2 Ni+1, delta Ms is equal to plus minus 1, delta Mi is equal to 0, capital A. Also, we should remember from this slide is also very much important. Splitting of energy levels, plus half, minus half, absorption signal, derivative of that G value will give you the position of the signal. Now, the magnitude of the splitting and the number of lines is depend upon, as I told you, in the hyperfine splitting. Now, this magnitude of this splitting, how much splitting will occur and how many number of lines will be there. So, number of lines, we told you, 2 Ni+1. And how much that magnitude of splitting will be there will be decided by 3 important things. Number 1 is the nuclear spin of the interacting nucleus. Nuclear spin of the interacting nucleus. Yes, because 2 Ni+1, if you put, suppose N is equal to 1, if you put I is equal to 1, you will get different results. You will get 3. If you put I is equal to half, you will get 2. If you put I is equal to, you get 4. So depending upon the spin of the nucleus, depending upon the spin of the nucleus, whether it is proton, half spin, it is nitrogen, 1 spin. So the number of lines or the magnitude will be depend. Second one is the nuclear gyromagnetic ratio. That is very important parameter which decides the magnitude of splitting in the ESR spectroscopy, hyperfine splitting. So what is that gyromagnetic ratio? It is a magnetic moment divided by angular moment of that particular electron, nucleus. Magnetic. It is the ratio of magnetic moment of the nucleus to the angular momentum of the nucleus. So that particular ratio is very much important for determining the magnitude of splitting. And third important important thing is the magnitude of the interaction between the electronic spin and the nuclear spin. How strongly the electronic spin and nuclear spins are interacting with each other will decide the magnitude or strength or how much that particular splitting will occur. This decreases with increase in the number of bonds between the nucleus and unpaired electron. If electron is present at suppose one carbon atom and the interacting non-zero spin having nucleus is very away from that, suppose 2-3 bonds away from that, then the interaction will be less between that unpaired electron or magnetic moment of unpaired electron and the magnetic moment of that proton or maybe that particular nucleus having non-zero spin. So this will be weak interaction. But whereas if that electron and that nucleus are near, separated by 1 bond or 2 bond, then there are more chances of interacting that 2 spins of electron and the nucleus, and magnitude of this splitting will be more. So in this way, friends, the magnitude of the splitting will depend upon the spin of the nucleus, the gyromagnetic ratio, and the distance, or we can say simply in rough crude language, we can say the distance between the interacting electron and the interacting nucleus. If these are near to each other, there will be more interaction, more magnitude of the splitting will be there. Otherwise, less splitting will be there. So almost now we have completed the basic principle and theory of this particular ESR spectroscopy, where we have studied, to just sum up the 2 important things we have studied. Number 1, that is a splitting of electronic spin states, splitting of electronic spin states in the magnetic field according to the Zeeman effect. And number 2, the hyperfine splitting because of interaction of the magnetic moment of the electron and the magnetic moment of the nuclei which are present nearby that electron and having non-zero spin. That particular interaction, the splitting is called as the hyperfine splitting. Now, coming to the application part. Actual examples. Now we will solve actual examples and we'll see how number of lines and intensities are calculated for different types of compounds which are paramagnetic. We'll see now one by one. Ashish sir.
Yes sir.
Ashish sir.
Yes sir.
आवाज वगैरे येत आहे माझा बरोबर सगळं ठीक
हो सर क्लिअर आहे हो सर
ठीक आहे Shall I proceed now?
Yes sir sure.
So there are type of molecules or substances which are paramagnetic in nature, but in order to have within this time in the today's lecture, I have tried to cover a variety of the examples, but particularly in this today's lecture, we'll see the radicals with hello, radicals with n equivalent nuclei with I is equal to half. We'll see some examples of this. That is, this is the compound of the substance which is paramagnetic and in which n equivalent nuclei are there having spin half. So hyperfine splitting like proton. Finally, we will see the radicals with n equivalent nuclei with I is equal to 1. For example, nitrogen. And we will see few examples of radicals with multiple hyperfine splitting. Apart from that, friends, there are hundreds of thousands of the organic molecules which are generated. There are electrochemical species which are generated in the situ, which are paramagnetic in nature, of which the electron paramagnetic resonance spectra is very much complicated and studied for the research purpose also. So first we will see radicals with n equivalent nuclei with I is equal to half. That is, spin is equal to half. This particular chart I have taken from some book and I have given the name of that book at the end of this presentation. So, and that this presentation I will share with you in our WhatsApp group after this lecture. So you can download that particular things. And most of the materials are also available free of cost on the internet. Now, first one is the electron paramagnetic resonance of radicals with n equivalent nuclei with I is equal to half. Now, this particular chart is very simple chart. This n is the number of nuclei. This is the number of nuclei. 0, 1, 2, 3, 4, 5. Number of nuclei having non-zero spin which are present nearby to our unpaired electron. That is, these are the nuclei which are interacting with our electron. Then, this particular capital N is the number of lines. Capital N is the number of lines. How many lines you will get? For example, in case of hydrogen atom, just now I have cited, there is only one nucleus, that is hydrogen proton, interacting with the electron. So we got two lines there, according to 2Ni plus 1. So number of nuclei interacting with the electron, and this is number of signals or the peaks we will get, number of lines we get. If it is, we will get one line, it is called as a singlet. So doublet, triplet, multiplet, like that. And this particular S is a number of transitions. How many transitions are possible? Number of transitions. So friends, for nuclei with I is equal to half, nuclei with I is equal to half, for nuclei with I is equal to half, if you put I is equal to half in 2Ni plus 1, so it will become 2 into N into half plus 1. So 2 will get cancelled. So it will become N plus 1. It will become N plus 1. So how many lines we get in the ESR spectra of the nuclei having half spin N plus 1? If there are 1 proton, we get 2 lines. 2 proton, 2 plus 1, 3 lines. 3 proton, 4 lines. Suppose CS3 radical, CS3 dot. Now that radical is present on the carbon and 3 protons are present on the same carbon. So therefore, they will interact 100% because they are on the same carbon atom. So this particular interaction will give you, now the proton, 3 hydrogens, they have spin half. So for half spin, you have N plus 1. That is 3 plus 1, 4 lines. So the ESR spectra of CS3 radical will give you how many lines? 4 lines. It will give you 4 lines. So in this way, we can interpret. So if you see here, what I told you here is 3 protons. 3 protons, we get 4 lines. This is called as a quartet. It's called as a quartet, like this. Now, this particular table also gives you the information. This particular part of the table gives you relative intensities. For the nuclei having half spin, the relative intensities follows the Pascal triangle for the intensity. So if you have a zero nuclei nearby the electron, then we will get only one line. That is a free electron. It is called as singlet and its intensity is 1. If there is one nucleus nearby the electron, for example, hydrogen atom, it will give you N plus 1, that is 2 lines. It is called as a doublet, and the intensity of line is this one here and this one, Pascal triangle, 1:2, 1:1, 1:1. If there are two protons or nuclei having half spin nearby the electron, then we'll get N plus 1, that is 2 plus 1, 3 lines, and the intensity is 1, 1 plus 1, 2, and this one here, that is 1:2, 2:1. If there are 3, for example, CH3 radical, then we'll get 3 plus 1, that is N plus 1, 3 plus 1, 4 lines, called as a quartet, and the intensity is for 4 lines, 1, 1 plus 3, and 1 here, 1:2, 3:2, 3:1, and so on. And so on. In this way, depending upon the number of nuclei having half spin, nearby or in vicinity to the unpaired electron which is under study, we get the number of lines. If there is a 1, 0, 1, 2, 3, 4, 5 like that, we get singlet, doublet, triplet and so on with the intensity determined from the Pascal triangle. So for nuclei with spin half, the number of lines is capital N is equal to N plus 1. It follows Pascal triangle, I is equal to half Pascal triangle for intensities, and capital S, that is number of transitions, is 2 raised to N, where N is the number of nuclei. So having this information with us, now we will proceed for the particular examples. Hydrogen atom, this we have already discussed. It contains a unpaired electron and a proton. The unpaired electron has magnetic moment. The spin gets split into external magnetic field into two lines like this, plus half and minus half. And because of that proton, one proton which is having spin half, now that proton of hydrogen atom and electron of hydrogen atom, their magnetic moment interact with each other and hyperfine splitting will occur into 2Ni plus 1, that is for half spin having nuclei N plus 1, that is 1 plus 1, 1 because one proton is there. So 1 plus 1, that is two lines. So each of this line, each of the Zeeman splitted line will further get split into two with plus up, minus up and plus up, minus up, having different energies, and transitions will occur according to the selection rule. The selection rule is, what is that selection rule? Delta Mi is equal to 0, that is transition will occur from plus up, minus up to minus up. Two transitions can occur. No other transition is possible here. These two transitions will have different energy of absorption in electromagnetic radiation, that is microwave region, and they will give the corresponding two signals, absorption signals, of which derivative signal will look like this. And for this particular electron, the G value is 2.0023. So friends, in this particular example of hydrogen atom, we get two lines, therefore doublet, and for doublet, you know the intensity is 1:1 according to this table. So doublet 1:1. It's two line doublet, one interacting nucleus is there. So this is the simple example of hydrogen atom. Moving further, a slightly complicated, that is methyl radical. Methyl radical. As I told you, here in case of the methyl radical, the electron is present on the carbon atom, and three protons are also directly attached to the carbon atom. So they will very strongly interact. I mean, the magnetic moment of the electron and the magnetic moment of the three protons will strongly interact with each other, because I told you earlier how the strength of interaction or magnitude of the splitting, hyperfine splitting is determined. One of the important parameter was the distance, actually bond distance between the electron and that particular nuclei. Here they are present on the same carbon atom. Therefore, these two already Zeeman splitted spin states of the electron will get split into how many? N plus 1, that is 3 plus 1, 4 lines, 1, 2, 3, 4 lines. This particular line will also get split into 1, 2, 3, 4 lines. So this is because of first proton, this is because of second proton, this is because of third proton. So if you drop this part also, there will not be any issue. You can directly write here 4 lines, 1, 2, 3, 4, means directly to understand. So you can also drop this particular point, this particular part. So 4 lines. Now there are 3 protons. 3 proton. One proton has a spin half. 2 proton have spin half plus half 1, and then for third half plus half is 3/2. So there will be a maximum value of this spin of nuclei is plus 3/2, then plus half, minus 3/2, and plus 3/2 plus half 3/2. So the corresponding Mi values, these are called as a Mi values. And friends, you know that the selection rule is delta Mi is equal to plus minus 0. Delta Mi is equal to 0. So you can draw any number of transition here, but that transition should follow delta Mi is equal to 0. And it has been observed that for this absorption spectrum, only 4 lines are possible, 4 transitions are possible. So nuclear spin state transitions among these electronic splitted, Zeeman splitted lines, energy levels, 4 possible lines are there according to that rule, delta Mi is equal to 0, and we get 1, 2, 3, 4 signals in the ESR spectrum. When you come to the table, there are 3 nuclei, that means you will get 4 lines, quartet, and the intensity is 1:3:3:1. You can see here 1:3:3:1. These two have same intensity. This is 1, 3, 3, 1. 1:3:3:1. Total number of lines 4. These lines are equally spaced, and friends, the distance, the spacing between these two, this one, and this one, is called as a hyperfine coupling constant. Hyperfine coupling constant, and this will also, that particular constant also will give you information about that compound. Coming to the next example. Yes, sir.
Yes, sir.
मॅडम आवाज वगैरे येत आहे ना व्यवस्थित?
हाँ, सब बढ़िया है सर.
So I will proceed now. Continue.
Okay, okay.
Now, just a slightly difficult example. Para-benzo-semiquinone radical anion. Para-benzo-semiquinone radical anion. I will request the MSc student not to bother about these diagrams and this particular complexity in the diagram. These are very simple to draw. Just if you follow that particular table, this one. So anybody can draw that. Just we have to remember our formula for I is equal to half nuclei, that is n plus 1, or in general 2ni plus 1, and we have to remember the selection rule. So then it is very easy. Para-benzo-semiquinone radical anion. This is the chemical structure of that particular molecule. Benzene, this is O dot and O negative. This is para-benzo-semiquinone radical anion. It has its own applications in different fields of science. Now, this, first of all, it is a paramagnetic species because it contains 1 unpaired electron. It contains a 1 unpaired electron. So therefore, this particular molecule will definitely give a response to the ESR spectrophotometer. Now, how? If you see here, this electron can, this electron can move, or because this is a doubly bonded system, so therefore it is a planar molecule, and the electron can move or can go through all these 6 carbon atoms and this oxygen also. So therefore, this electron can come here also, will interact with this proton, and it will interact with all the 4 protons, and all the 4 protons are also equivalent. They are same, their chemical environment is same. So therefore, how many nuclei are there? This oxygen is not having the spin, it is having a 0 spin oxygen. So therefore, this will not interact with the oxygen because we require the non-zero spin having nuclei. Why? Because non-zero spin having nuclei, which is not 0, and if it is have a spin, it will have a angular momentum. It will have a magnetic field. It will develop a magnetic field or magnetic moment, and that magnetic moment interacts with our electrons' magnetic moment, and hyperfine splitting will occur. So this 4, and carbon generally it is 6 carbon 12 because its abundance is more than 99%. So therefore carbon 13 is very less. So this carbon is also having 0 spin, oxygen is having also 0 spin, and hydrogen. So there are only 3 types of atoms here: carbon, hydrogen, oxygen. So oxygen, carbon, no question. Hydrogen is having half spin. So therefore it will produce its magnetic moment and interact with the magnetic moment of the electron, and therefore hyperfine splitting will be observed over here. So what happened, friends? All these 4 hydrogen are equivalent. Coming to the table again, there are 4 non-zero spin having nuclei. So we will get 5 lines, which is called as a quintet. And the intensity of that line, according to the Pascal triangle, is 1:4:6:4:1, and that is what we have observed over here. If you see here, is plus minus half, that is a spin state, degenerate spin state of the electron, which has been get splitted into two, plus half and minus half, counter current, opposite and aligned to the external magnetic field in presence of magnetic field. You can drop this part, no issue. And each of these two lines, this line and this line, this spin state of electron and this spin state of electron will get splitted into n+1 lines. That is 4 plus 1. Why 4? Because 1, 2, 3, 4 equivalent protons are there. 4 plus 1, 5 lines. You can see here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Each of the two Zeeman splitted spin state of the electron have now been splitted further into n+1, that is 4 plus 1 is equal to 5 lines. We got here 10 total lines, and when we have applied the selection rule, that is delta mi is equal to 0, for the transition among these 10 lines, it has been observed that only 5 lines can be drawn, which follows this delta mi is equal to 0 selection rule. There are 5 protons. This proton half spin plus half 1 plus half 3/2 plus half 2. So total spin of that 4 protons is 2. So therefore 2, 1, 0, 1 and 2. 2, minus 2, 1, 0, minus 1, minus 2. That is the different combinations of, these are the different combinations of the spin combinations of the 4 interacting protons having non-zero spin or half spin. So in this way, it will give you the 5 lines, 1, 2, 3, 4, 5. This is the first derivative, and the intensity is 1:4:6:4:1. You can see this. Another example you can see where interacting nucleus is hydrogen, that is half, having I is equal to half. It is cyclopentadienyl radical. Cyclopentadienyl radical. This is a cyclopentadienyl radical, and this is again there are carbon and hydrogens only. Carbon has 0 spin. This particular electron can move here on all the carbon atom and can interact with all the 5 protons. Now there are 5 protons. So instead of going into more detail, we have now shown here 5 protons. All the 5 protons are equivalent, because the structure is very much symmetric. All the protons are, carbons are same, hydrogens are same, equivalent. Therefore, this will give you n+1, that is 5 plus 1, 6 lines, 1, 2, 3, 4, 5 and 6. So 6 lines, and that is called as a sectate. And if you come to the table again, 5 protons or 5 nuclei having half spin, 5 nuclei having half spin is there, we'll get 6 lines. It is called as a sextate. And the intensity is 1:5:10:10:5:1. So in this way, friends, we can now very easily draw or determine the number of lines and the intensity and the number of transitions in any molecule, any organic molecule, which is a paramagnetic, and it contains at least 100 electron. It is a radical, and it is interacting with the nuclei with spin half. It may be hydrogen, that is proton, or any other nuclei having half spin. Just the number of protons are increasing. This is a benzene anion radical. Benzene anion radical. In earlier example, 5 equivalent protons were there. Here, 6 equivalent protons are there. Carbon has non-zero spin, so therefore, this particular electron's magnetic moment will not interact with the carbon, because in carbon it has a zero spin. But the hydrogen's magnetic moment, this proton's magnetic moment, will interact with the magnetic moment of this electron, and hyperfine splitting will occur in this benzene radical, anion radical, and this will give you, being all the 6 protons equivalent, this will give you n+1, that is 6 plus 1 is equal to 7 lines, 1, 2, 3, 4, 5, 6, 7. If you go to the table again, there is no issue. It will give you 6 protons or 6 nuclei having half spin, will give you 7 lines called as a septate. 1:6:15:20:15:6:1, according to the Pascal triangle, because as you know that For the nuclei having half spin, the intensity of the signals in the ESR spectroscopy follow the Pascal triangle. Cyclopenta-trinyl neutral radical. Again, the same case is there. There are 7 protons. We'll get the 8 lines, 1, 2, 3, 4, 5, 6, 7 and 8 lines. So cyclopenta-trinyl neutral anion. So from here you can see 5 proton cyclopentadienyl radical, 6 proton benzene anion radical, 7 proton cyclopentatetranyl. So 7 protons, and this is a 8 proton cyclooctatetraene anion radical. So again it will follow the Pascal triangle for intensity, your n+1 rule for the number of lines or the number of transitions. So this will give you 9 lines, 1, 2, 3, 4, 5, 6, 7, 8 and 9 lines. So it will give you 9 lines. So now this particular, it proves there are 8 equivalent hydrogen and proves the flat structure of anion while the neutral molecule is not plane. So see, this is the application or beauty of the ESR spectroscopy. This neutral molecule, this particular molecule, if it is neutral, then it is not a planar. It is not planar molecule. But when it is a anion radical, then it is giving you ESR spectra, number 1, and it is giving you 9 lines indicating that this particular electron is interacting with all the hydrogen atoms and equivalently all the protons are equivalent. So therefore it is a flat structure, that is a planar structure of this particular anion radical. Cyclooctatetraene anion radical can be studied by the ESR spectroscopy. So we will get here 8 + 1, 9 lines. Now slightly different example. In all these examples we have studied the hydrocarbons mainly, and n+1 rule we have used. Now hydroxyl methyl neutral radical. Hydroxyl methyl neutral radical. Now friends, you can see here 2 different types of protons are there. That is this methyl proton, methylene proton, Ch2, and this hydroxyl proton. But this hydroxyl proton exchanges continuously with the solvent rapidly. It exchanges, and therefore the magnetic moment of this this electron does not interact with the magnetic moment of this proton. It interacts only with these 2 protons. So 2 + 1, it will give you simply a 3-line ESR spectrum. This is the derivative spectrum, 1:2:1 according to our Pascal triangle. Intensities 1:2:1. And this particular electron magnetic moment does not interact with this proton. Oxygen, no issue because it has a 0 spin. Naphthalene radical anion. Naphthalene radical anion. Paramagnetic in nature, and it contains 1, 2, 3, 4. 1, 2, 3, 4. 4 protons and 4 protons. So here we have to apply n+1 into m+1 rule, because these 4 protons will give you 4 + 1, 5 lines, and these 4 protons will give you m+1, that is 4 + 1, 5 lines, 5 into 5, so we'll get 25 lines in the naphthalene radical anion. So here, with this, we have completed one part, that is as examples, that is the ESR spectra of the nuclei or radicals containing interacting nuclei with spin is equal to half. The second part we will consider now, spin is equal to 1, and then we can have the topic for discussion. The second part is electron paramagnetic resonance spectroscopy of radicals with n equivalent nuclei with I is equal to 1. I is equal to 1. I is equal to half we have already studied. Now I is equal to 1 is a 7 nitrogen 14. This is a particular space atom nucleus having spin 1, or your deuterium 1H2 deuterium having spin 1. So the relative densities, number of signals and number of transitions are given here for I is equal to 1. Again, if you see this table, N, number of interacting nuclei having spin I is equal to 1. 1, 2, 3, 4, 5. Capital N, number of lines, and S, number of transitions. So if there is a one nucleus having I is equal to 1, then it will split each of the Zeeman splitted spin state of the electron into 3 lines. So we'll get 6 lines for plus half spin state of the electron and 3 for minus half spin state of the electron. So and so on. So 2, then we'll get 5 lines, because our basic formula is 2Ni plus 1. 2Ni plus 1. So you get 2N into 1 plus 1. That is 2N plus 1. 2N plus 1. 2N plus 1, that is shown here, number of lines. 2N plus 1. So if there is a 1 nitrogen, suppose, then N is 1. 2 into 1 plus 1. 3 lines. It will give you 3 lines. If there are 2 nitrogens nearby the unpaired electron, 2 into 2, 4 plus 1, we get 5 lines. 3 to the 6 plus 1, 7, and so on. 9. How 9? 4 into 2, 8. 4 to the 8 plus 1, 9. Intensities, relative intensities, which have been determined. This is not this particular nuclei will not follow the Pascal triangle, because this particular intensities ratio for the different signals is obtained from the strength of the magnetic moment of the nuclei. First example is one of the nitroxide, popularly known as TEMPO, tempo, 2266 tetramethyl piperidine 1-il oxide. It's called as a tempo, and this is the structure of that particular radical. This radical is now interacts with this nitrogen, and this will not interact with this protons 6 and this 612 proton, because the distance is bond number 1, 2, 3, 4, almost 3-4 bond distance is there. As I told you, as we know, the number of bond separation or the distance between the interacting electron and the nucleus, as it increases, the magnitude of the splitting will decreases, and according to that particular rule or thing, this electron does not interact with all these protons. Here also 2 protons are there, here 2 protons are there, but it only interacts with the which is having spin 1. Oxygen has 0 spin, means oxygen nucleus has 0. Hydrogen have half spin, but they are away from the this particular radical, so therefore it will interact only with the nitrogen spin, and when it interact with nitrogen spin, the formula is 2N plus 1, that is 2N is number of nuclei having spin 1 nearby the electron. There is only one nuclei, N, that is 1. So 2 into 1 plus 1 is equal to 3 lines. We will get 3 line spectrum. That is, these 2, each of the 2 Zeeman splitted lines, or each of the 2 Zeeman splitted spin states of the electron will further get splitted into 3 and 3 lines. We'll get 6 total lines, and among that, according to delta Mi is equal to 0. Delta Mi is equal to 0. According to this selection rule, there are only 3 transition possibles, that is -1 to -1, +1 to 0 to 0, and +1 to +1. You can draw any transition. This will not definitely follow delta Mi is equal to 0 selection rule. So therefore, there are only 3 transitions. Each of the transition has a specific energy, particular energy in the electromagnetic radiation. That is in the microwave region of the EMR, electromagnetic radiation, and it will give you 3 signals, equally spaced 3 signals, and with the equal intensity, because you can see here for triplet there is a 1:1:1. When 1 nitrogen, 1:1:1, that we have to remember. Particularly for the PG students, those who are appearing for different competitive exams like NET or GATE or SET exam, then such type of examples are asked, and generally when we write triplet, we think about the intensity 1:2:1. But as I told you, depending upon the magnetic moment of the nucleus, for example, nucleus having half spin and nucleus having 1 spin, the strength of the magnetic moment increases or changes. So that strength is different. So therefore, depending upon the strength of the magnetic moment, that particular intensities of the signals also changes. So that we have to remember for nuclei having spin 1, this intensities and one nucleus, this is 1:2. These are same 1:2, 1:1. You can see here. I will give you this presentation. I will share this presentation with all of you after this lecture. Another one you can see here is a di-butyl nitroxide neutral radical. This is CH3/3, CH3/3, NO. Here also you can see this particular proton, this particular electron's magnetic field or electron's magnetic moment does not interact with this 9 and these 9 protons, because 1, 2 and 3 to 4 bond separation is there. They will away from this. They are not vicinity or nearby this electron. Therefore, this 9 protons or these 9 protons will not split the Zeeman splitted spin states of this electron, but this nitrogen will definitely, because this is directly interacting with this nitrogen having spin 1 and only one nitrogen is there, will definitely split the spin states, each of the 2 spin states of the electron into 2n plus 1, that is 2 into 1 plus 1, that is 3 lines, and we'll get same this type of the splitting pattern, and we'll get 3 lines of equal intensity, that is 1:1. Sometimes we consider the splitting with these protons, but you have to remember that if the bond separation is more than 2 or 3, then, and if it is a sp3 hybridized atoms, then there is difficult for this proton, this particular unpaired electron to delocalize or reach up to that particular nucleus. If there is a sp2 or sp hybridized structure, fully hybridized structure, then that particular charge or the radical or electron can circulate, or this can delocalize among all the atoms, and this can interact. Here there is no question of interaction of this magnetic moment of electron and magnetic moment of this 9 proton, because there is a long distance, as well as these carbons are sp3 hybridized, and there is no way for the delocalization of this particular electron on these carbons. And another one example is a substituted hello, Ashish sir. Hello,
Sir, you are audible, sir.
Yes, sir.
yeah. How much time is there for me?
It's about,
Is there any time limit?
sir, 1.5 hours there.
याच्यानंतर किती वेळ आहे माझ्यासाठी अजून?
सर टाइम जवळपास संपलेला आहे सर.
Okay, just give me 15 minutes, sir.
Okay, sir, no problem.
10 to 15 minutes, I will finish my lecture.
Okay, sir.
10 to 15 minutes. Please unmute yourself, all of you. Substituted nitronil nitroxide neutral radical. This particular substance is there. Here we are getting 5 lines. Because carbons, there is no question, because the 0 spin, nitrogen 1 spin, these 2 nitrogens are there, and again this 6 proton and these 6 protons are away from this particular radical, and this is also away. So therefore this particular radical interacts with the 2 nitrogens in this structure. It interacts with this bond, flanking can be done, this bond can come here and radical can go there. So therefore this interacts with 2 nitrogen, and you can see here, friends, clearly if there are 2 nuclei having spin 1, then we'll give you 5 lines with intensity 1:2:3:2:1, and the same 2:3:1, 5 lines we got in this for this structure. Another one example with nuclei having spin 1 is a tetracyanoethene anion radical. So you can see CN, the tetracyano. Ethene, this is a ethene, and this is a dot negative anion radical. Tetracyanoethene anion radical. Now there are 1, 2, 3, 4 nitrogens, and definitely this electron can interact with any one of these nitrogens, because this is a fully planar structure. sp2 and sp hybridized atoms are there. So the delocalization of electron among all the 4 nitrogen is possible. So therefore this electron's magnetic moment interact with all the 4 nitrogens, nucleus magnetic moment, nitrogen nuclear magnetic moment, and splitting of the lines will take place for the 4 atoms. We have total 9 lines. Because if you put 2n plus 1, 2 into 4, 8 plus 1, 9. Or even if you put 2ni plus 1 in that equation also, 2 into 4, 8 into 1 plus 1, that is 9 lines we'll get. So here we get 9 lines. 1, 2, 3, 4, 5, 6, 7, 8 and 9 lines. The intensity ratio is 1:4:10:16:19:10:4:1. So this is tetracino. So therefore, friends, the pattern of the spectrum is useful for determining the structure of the various radicals. This is the application particularly of the ESR spectroscopy. Lastly, so first we have studied the ESR spectra of radicals with I is equal to half. Second, we have studied ESR spectra of radicals with I is equal to 1. Then lastly, electron paramagnetic resonance of radicals with multiple hyperfine splitting. Only one examples I have quoted here because of the time factor, but a number of examples are available in the books. I will tell you the list of books also that is listed over here, so you can go through that. Here, multiple hyperfine splitting means there are different type of nuclei. All the nuclei interacting with the electron's magnetic moment are not equivalent. For example, CH2OH, CH2OH. Now these 2 protons, methylene protons are these 2 methylene proton and this OH proton. So if in case of the no exchange of this proton with the solvent, if in this structure, if it is possible, then it will give you a doublet, that is 2 lines because of this 1 proton, n plus 1, 2 lines, and because of these 2 protons we get 3 lines. So that 3 lines, 1, 2, 3 will get split into doublet 2 lines. In this way we will get the 6 lines with the intensity ratio here 1:2:1. So this is somewhat complex structure because here 2 different types of protons are there. This will give you triplet 1, 2, 3. Each of that 3 lines will get split into 2 lines, doublet, doublet, doublet. This is called as a triplet of doublets. So we'll run fast now. What we can learn from ESR is we can study the unpaired electrons, its type, nature, surrounding and environment and behavior of that particular species or the electron. The fine structure, that is splitting of the electron spin state into 2 due to Zeeman effect in presence of external magnetic field, that is called as a fine structure, will represent the interaction between electron and electron. Hyperfine structure, that is because of the interaction of magnetic moment of the electron and the magnetic moment of the nuclei having non-zero spin which are near to that paramagnetic electron. So that is hyperfine structure, gives you the information about the interaction between electrons and nuclei. The G value give you the value of absorption signal, and it will also reflect the orbital level occupied by the electron. The line width of the signals is relaxation time, and the saturation characteristics are related to the longitudinal relaxation times. As I told you, any paramagnetic species, it may be a free radical, it may be an inorganic metal complexes containing unpaired electron, organic paramagnetic organic radicals, or the radicals or the species, paramagnetic species generated in the electrochemical oxidation or reduction. This can be studied by the ESR spectroscopy. Their structure can be characterized by using the structure, and their geometry can be studied by using the ESR spectroscopy. But apart from that, in general, it gives you the electron state. It gives you, is helpful for studying the impurities in the semiconductor lattice, defects in the lattice, structure of glass and amorphous materials, for studying and tracking the catalytic reactions which involve the paramagnetic species or radicals, changes in the charge state, photocatalytic reactivity and photochemical reaction mechanism, radical polymerization, polymer resolution, active oxygen radicals related to the aging in disease in living organisms, oxidative degradation of lipids, detection of foodstuffs, exposure to radiation, measurement of age of the fossils, and geological features using lattice defects. These are the some common books, the references I have used: Banwell, Fundamentals of Molecular Spectroscopy, and Wikipedia. This particular document is available free of cost on the internet. This is very good document. I have also referred that, and all the free access material that is available on the internet. I acknowledge the Rajiv Gandhi Science and Technology Commission, Government of Maharashtra, Mumbai, for their funds for our university and for me for performing the research. University Grant Commission, New Delhi, for their funds, and our Swami Ramananda Tirtha, Marathwada University, Nanded, particularly, and our Honorable Vice Chancellor, sir, who is active and dynamic person and visionary person for development of our university. These are our research fellows. Thank you. Thank you, sir. Bye.
Thank you so much, sir, for your valuable discussion.
Thank you.
Now I would like to request Dr. Pradeep Tekare, sir, to deliver his lecture.
Am I audible?
Yes, sir.
Am I audible?
Yes, sir.
Proceed. Shall I start?
Yeah, yes, sir.
Hello.
Yes, sir, I can hear you.
Okay, Devsarkar sir, you are presenting
Yes.
now. Please remove your screen so that I can share my screen.
Okay.
Stop sharing, कीजिए, sir.
Okay.
Stop sharing,
Yes,
कीजिए,
yes.
sir.
Yes.
Okay, sir.
Okay, good morning to all of you. Yes, am I audible?
Yes, sir, we can hear you. You can continue.
Yeah. Okay. So I am very much thankful to the principal, Dr. Kaya sir, Head of the department, chemistry department, my friend Dr. Shaukat Shah, my friend Ashish Vakudkar, Professor Ashish Vakudkar, Professor Sandeep, Priyanka Madam, Professor Avinash, and all the faculty. It is nice to hear the lecture of my friend Dr. Santosh Devsarkar. And now with the permission of organizer, I am going to start the lecture. As Dr. Santosh Devsarkar told in his lecture that NMR and ESR are spin resonance spectroscopy, and he focused particularly on ESR spectroscopy. All of you know that the spectroscopy is the branch of which deals with the study of interaction of electromagnetic radiations with matter. As far as the organic chemistry is concerned, for the characterization of the newly synthesized compound, particularly I am talking about the organic compound, mainly 4 spectroscopic techniques are needed. They are UV visible spectroscopy, that is ultraviolet visible spectroscopy, infrared spectroscopy, IR spectroscopy, then NMR spectroscopy. Under NMR, proton magnetic resonance and C13 magnetic resonance spectroscopic techniques are there, and the 4th technique is a mass spectroscopic technique. You also aware about the functions or the of this spectroscopic technique. UV visible spectroscopy is useful for the carbon-carbon double bond, means to identify the presence of whether the compound there is a conjugation or not. Infrared spectroscopy gives us the information about the functional group present in the compound. Then NMR spectroscopy, that is PMR, gives us the information about the number of hydrogens present in the compound, as well as it gives us the information about the different magnetic and electronic environment, means the particular situation, the position of that hydrogen atoms in the compound. And C13 magnetic resonance gives us the information about the number of carbons and their surrounding. You know that the NMR is the actually no one spectroscopic technique is sufficient to complete characterization, to give the complete elucidation of the organic compound. For the compound to be completely characterized, there is a need of spectroscopic technique, that is the visible spectroscopy, IR spectroscopy, in NMR, proton magnetic and C13 magnetic resonance spectroscopy, and 4th one is the mass spectroscopic technique. After characterization of the organic compound by using this UV visible, IR, NMR, finally we have to characterize the compound with the help of mass spectroscopy by the fragmentation process. Today the topic allotted to me is the NMR spectroscopy, that is PMR and C13. In the first presentation, I am going to discuss on the PMR spectroscopic technique, and in the second presentation, we will have a look on C13 spectroscopic technique. Particularly at this presentation,
Yeah.
Yes. Yes, sir.
Right from the first the presentation, okay. So, firstly, we will see some aspects of NMR spectroscopy that you have already discussed in your UG curriculum. The types of NMR spectroscopy, that is the number of what is chemical shift, and spin splitting, coupling constant, etc. And the next part of my presentation, we will have a look on topic of NMR spectroscopy, that's spin decoupling, nuclear Overhauser effect, first order spectra, car plus equation, then two-dimensional NMR spectroscopy, that is Cauchy, noisy, and head core spectroscopy. Okay, so shall we proceed? Ashish sir?
Sure, sir.
Yeah, okay. So NMR spectroscopy is first time in 1950. We know that E.M. Purcell and Felix Bloch got the Nobel Prize for this NMR spectroscopy. And it is, as I told you, as Dr. Devsarkar in the first lecture told you that it is a spin resonance spectroscopy. Okay, now which nucleus are to be, see this table, the NMR, the element from the periodic table which have essentially the mass number odd are said to be NMR active. See, if the mass number is odd and atomic number is odd or even, in that case, the mass number is odd and atomic number is odd. In that case, the spin quantum number value is half integer, that is 1/2, 3/2, 5/2. If both the mass number and atomic number are even, in that case the I value is 0. And when the mass number is even and atomic number is odd, in that case the spin value is integer, that is 1, 2, 3. Okay, and remember that nucleus which have the half spin value are responsible for the NMR active. Okay, thereby if you think about the hydrogen and carbon, hydrogen atomic number is 1, mass number is 1, so both are odd, spin value is I, that is equal to half, and hence it is NMR active, PMR, that is proton magnetic resonance. In case of 6C12, 6, that is the even number, 12, it is also even number, so carbon having even mass number and atomic number even, spin value is 0 and is not NMR active. However, the isotope of carbon, that is C13, having the mass number odd, is NMR active. Okay, so 1H1 and 6C13 are the NMR active, while 6C12 carbon is having even mass and atom. Okay, then let's come to the principle of the NMR spectroscopy. The nucleus of the hydrogen atom or any nucleus which obeys the rule which I have talked on the previous slide. The nucleus of this atom behaves as a tiny bar magnet, and it does so because it possesses both electric charges and mechanical spin. Any spinning charge body will generate a magnetic field. Thus, the hydrogen having a number also generate a magnetic field. Okay, now the precessing proton will only absorb energy from RF source, that is the radio frequency source. Before moving to this point, let me tell you about what is the precessional frequency. When a spinning nucleus is placed in external magnetic field, it tries to align in the direction of magnetic field, but due to spinning motion, it cannot orient in the direction of field. However, it starts rotating at a particular angle along the direction of field. This is called as a precessional motion, and the frequency of rotation is called as a precessional frequency. Okay, means we can consider the example of null frequency. Okay, means we can consider the example of top, moving top. When we move that top, first is it rotates about its own axis, and when at the point when you get down, at that time it moves along its own axis as well as it moves in this fashion in the particular orbit. That motion is called as a precessional motion, moving of the top. Okay, you can imagine that. That is called as a precessional motion. The precessing proton. Okay, so you know now the precessional frequency and the precessional motion, precessional orbit. That precessing proton will only absorb the energy from radio frequency source if the frequency of radio frequency beam. At that time, the absorption takes place. The nucleus and RF beam said to be in the resonance. That absorption means the nucleus and RF beam. There is a mistake. It's BEAM actually. That said to be in resonance. Hence, the term is nuclear magnetic resonance. We record this absorption of energy in the form of NMR spectrum. We will see in detail of this NMR spectrum afterwards. This precessional motion can be in or opposite to the direction of applied magnetic field. So the allowed energy level split into two states. Lower value corresponding to plus half and the higher value corresponding to minus half. You can see in this diagram that there are two energy levels. So the lower one is having the energy value plus half, and the higher means upper is having minus half. As the strength of the applied field increases, the energy separation is also increases. I am repeating again. As the strength of the applied magnetic field increases, the energy separation between these two energy levels will also increase. These two states have different energies, and separation means there is an energy gap, there is a separation of energy between them. In NMR spectroscopy, the magnetic field is applied to nuclei to split the energy levels. It is irradiated with the radio waves of a definite frequency. When this frequency matches with the energy gap, at that time the absorption takes place. I am repeating again, the magnetic field is applied from the perpendicular position to the radio frequency waves, and when that energy gap matches with the frequency of the radio frequency waves, at that time absorption takes place. And from this absorption, the signal is obtained in the NMR spectrum. And thereby it is possible to get the structural information of the molecule. Okay, so I am repeating again in short that here the nucleus is considered as a tiny bar magnet. It is placed in between the two poles, that is south and north pole you can see here, and external magnetic field is generated, and when such nucleus, and then we get the NMR spectrum. The principle of 1H NMR and C13 NMR is same. Okay. After the lecture, if any difficulty is there, we will discuss about that. This is again the picture showing the spin motion, how the nucleus is spin and generates the induced dipole moment that is shown here. Okay. Now coming to the next point, in short, we will see about the instrumentation. In order to record the NMR spectrum, a constant radio frequency is supplied from a radio frequency generator. The commonly used frequency is are 60 megahertz, 100 megahertz, and 200 megahertz. The magnetic field is varied. It depends. Means you can increase or decrease it accordingly. As soon as the splitting energy, that is a gap between the ground state and excited state, that is delta E, matches with the supplied radio frequency wave, then at that time the proton, in case of proton resonance, proton, that is hydrogen, absorb this frequency by the recorder, and we get the spectrum, that is PMR spectrum or NMR spectrum. Okay, actually it is a easy part, just I am reversing the knowledge, then we will move to the advanced part of the NMR spectroscopy. Okay, then let us see the important aspects of NMR spectroscopy. First one is the about the number of signals. For that, we must have the idea about the equivalent and non-equivalent protons. See, in case of benzene, you can see on your screen that all the 6 hydrogen atoms are in the same surrounding. That's why they form one set of signal, and we get one PMR spectrum. Sorry, one signal in the PMR. See this one, just a minute. Yes. Now see this compound, that is 2-chloropropane. Here 2 types of protons are there. You can see these methyl protons and these 2 methyl protons are in the same surrounding. So these 6 protons form one set of protons, and thereby giving one signal in the PMR. And this is the CH group, it gives the another signal. So 2 PMR signals we will get. Okay, same you can see here for CH3 we get one. These 2 CH2 are not same, they are different because they have different chemical environment. As you can see here that this CH2 group is sandwiched between the methyl and methylene group. However, this CH2 group is trapped between CH2 and Cl. So here these CH2 groups are different. So overall 3 NMR signals are obtained. We know about these things. Okay, so depending upon this, I want to ask 1 or 2 questions, particularly to the PG students. Such type of questions are always asked in the CETNET examination. That, for example, how will you distinguish between ethanol and dimethyl ether by using PMR spectroscopy? See, the question is, how will you distinguish and CH3OCH3, that is dimethyl ether, by using the PMR spectroscopy? Any of the APG student can unmute herself or himself and can try for this. How will you distinguish between these 2 compounds? It is a very simple question. Okay, so on the basis of number of protons, number of signals obtained in the PMR spectroscopy, we can classify them. We can distinguish between these 2 compounds. They have the same molecular formula, only the functional group is different. See here, two signals will obtain. This is one for the methyl group and another for methylene, and 3 signals, third for OH proton. However, in case of dimethyl ether, you can see that these 2 methyl groups are in the same surrounding as the oxygen is there, sandwiched between these 2 methyl. They have the same surrounding. Therefore, they form the set of 6 protons, giving only one signal. So in this way, by the help of PMR spectroscopy, we can distinguish between any 2 compounds depending upon the number of signals obtained. Okay, is it clear? Such type of examples may ask in the examinations always. Okay, now next point is intensity of the signal. Area under the signal is called as the intensity of the signal, and it is directly proportional to the number of protons constituting that particular signal. Means suppose, let me show you the example in the previous slide. Yes. Yes, see here the three signals you can see in this spectrum. That the intensity, the height of these three signals is not same. They are of different height. So it is directly proportional to the number of hydrogen constituting that particular signal. That is the second aspect of NMR spectroscopy. Now the third aspect of the NMR spectroscopy is chemical shift. What do you mean by chemical shift? Before that, let us have the discussion on the position of signals. So any proton undergoes resonance when the applied field strength, or we can say frequency, matches with the energy separation between two levels. In actual practice, the frequency is kept constant and applied field strength is increased continuously. There are both ways actually. You can keep the radio frequency constant and can change the H value, that is magnetic field. Or second option is that you can keep the magnetic field constant and you can change the radio frequency. The magnetic field experienced by all proton is not same. I am repeating the sentence again. The magnetic field experienced by all the protons in the particular molecule is not same. It depends on its electronic environment. For example, if I talk about the CH3, CH2OH, then there are three types of protons: CH3 protons, CH2 protons, and OH protons, and all experience the different electronic environment. Electrons in a molecule produce their own field around the proton. This is called as the secondary field, or which is also called as the induced magnetic field. If this secondary magnetic field opposes the applied magnetic field, the effective magnetic field decreases. I am repeating again. If the secondary magnetic field, that is induced magnetic field produced by the nucleus, opposes the applied field, external magnetic field, then the effective magnetic field decreases. Such proton is called as a shielded proton. Such proton has called as a shielded by the vicinity of the electron, And if it is opposite, if it is in the same direction, then it is called as a deshielded proton. Okay, so the position of the peak in an NMR spectrum relative to the reference peak is expressed in terms of the chemical shift, that is delta. And it is a dimensionless quantity. There is no unit for delta. Another unit, previously used unit for the same, is a tau. You can see the relation here, the tau is equal to 10 minus a delta, the relation between tau and delta. Okay, and this is the equation which is given. You can see delta is equal to magnetic field of the reference and minus magnetic field of sample divided by magnetic field of the reference multiplied by 10 to the power 6 ppm. You will see some numericals based on this also in later slides. Okay, so this is about the deshielding. Then in the slide we have discussed about the formula for the calculation of delta, and here you can see reference is there. So which reference compound is used in the NMR spectroscopy? All of you have the idea. That is tetramethylsilane. That is the compound in which the silicon is there and which is attached to 4 methyl groups. You have the idea about this also, that OMS is used as a reference in the NMR spectroscopy. You know about this, that it is an inert compound. It gives a sharp signal, and as the proton date, they appear right side, and that point we considered as a zero. Okay, and hence the tetramethylsilane is used as a reference compound. Secondly, it is soluble in almost all the organic compounds. Okay, then continuing to the previous point of a chemical shift, shielding, deshielding. What are the factors influencing the chemical shift? See, before that, see this spectrum, which is divided. We can see here the shielded region is called as a filled region, and the deshielded region is called as a downfilled region. At 0, we get this signal of the tetramethylsilane, and from 0 to 10 onward also you can get this peak, 11, 12 in case of lead and OH. So we get the different signals, different signals. Now, what are the factors which affect the electronegativity, which defect the chemical shift of the NMR? The first is electronegativity and second is anisotropic effect. There are other factors also, but we will concentrate only on these two. All of you know about the electronegativity, that if the electronegative atom like iodine, bromine, chlorine, fluorine, oxygen, nitrogen, etc. are attached, in that case there is a deshielding. Deshielding means the signal appears at high delta value. Particularly, let me show you the these delta values which are used as a standard reference. See, you can see for the methyl delta value is 0.9, but if the methyl is attached to carbon-carbon double bond, then it is 1.6. If the carbonyl group is attached to the methyl group, then the value is 2.1. If it is attached to nitrogen, then 2.2. See, the basic value is 0.9, and all the remaining values which are given in this particular table, they are more than 0.9. It means that there is a deshielding. So electronegativity of the adjacent atom, neighboring atom like nitrogen, oxygen, or halogen atom, due to that the deshielding takes place and the signal moves toward the downfield region. Okay, so coming to our point again, so electronegativity, it is very clear to all of you. I know that. Now let's have the look on the anisotropic effect. The carbon atom in acetylene. Let us see about the acetylene first. It is in the next slide. Yes. This is the acetylene molecule. Okay, so carbon atom in the acetylene is more electronegative. Why it is more electronegative? If you compare the electronegativity of the carbon between acetylene, ethylene, and ethane. Acetylene, carbon-carbon triple bonded compound. Okay. Ethylene, I can write structure here. CH2 double bond CH2. And ethane, CH3, CH3. Okay. So, what is the hybridization rate of the carbon? It is sp hybridized. And carbon in ethylene is sp2 hybridized. And the carbon in ethane is sp3 hybridized. What is the percentage of S character in the sp2 and sp3? In sp, the percentage of S character, one is S and other is P. So it is obvious it is 50% S character. In case of carbon, in ethylene having sp2 hybridization, the S character is sp2, one is S and two are P. So it is 33.33%. However, the S characters in the methane, the carbon of the methane, having the sp3 hybridization is 25%. In acetylene, the carbon has the 50% S character. In ethylene, the carbon have 33.33% S character, and in ethane, the carbon have the 25% S character. Now remember, more the S character, more is the electronegativity. So which carbon is more electronegative? When you compare these three compounds, that is alkyne, alkene, and alkene. Obviously, it is a alkyne, that is acetylene, here in this example, which have more electronegative nature. Okay, as it is sp hybridized. Okay, but now as it is a more electronegative, it is expected that the hydrogen attached to this carbon of the acetylene should be deshielded, because in the previous factor, that is electronegativity, we already discussed about this, that when the hydrogen, when the electronegative atom is attached, in that case, the deshielding takes place. But here, the different thing is there. The carbon atom in acetylene is more electronegative than the carbon atom in ethylene and the carbon atom in alkane, till the carbon in acetylene is shows shielding effect. It is important. But the chemical shift value for acetylenic protons are less, means more shielded than the ethylenic protons. Such anomalous behavior can be explained by the anisotropic effect, which is produced by the circulation of pi electrons under the influence of applied magnetic field. What is the factor responsible for this? Why this anomalous behavior is there? Due to the circulation of pi electrons under the influence of applied magnetic field. What is meant by anisotropy? Anisotropy, just a minute. Let us come to that. Yes, this is. What is the meaning of this anisotropy? Anisotropy means uneven magnetic field in space. Uneven magnetic space, the magnetic field, that is called as anisotropy. And that is a different region of space are characterized by different magnetic field strength. The anisotropic effect depends upon the orientation of the molecule with respect to the applied field. In fact, a proton experiences three different fields. The applied field generated by the pi electrons, in case of, you can see here, ethylene, then in case of aromatic compound. Okay, so that field generated by the pi electrons. Other is the induced magnetic field generated by sigma electrons. Okay, the pi electrons are more polarizable. We know that the pi electrons are more polarizable than the sigma bonds. Therefore, the induced magnetic field due to the pi electron movement is stronger than the induced magnetic field generated by sigma bond. I am repeating again. The induced magnetic field generated by the pi electrons is more as compared to sigma electrons. And depending on the position of the proton in the induced magnetic field, it can be have this smaller delta value, that is a shielded region, or higher delta value, that is a deshielded region. Okay, so it will be clear by seeing the examples in upcoming slides. Here you can see in this slide that the benzene highly deshielded and the hydrogens, that is protons, are appeared in the region 6.5 to 8 delta value. In case of ethylene also you can see deshielding, and hydrogens are appear in between 4.5 to 6 delta value. So both are deshielding. This picture clearly convinces you that how the induced magnetic field produced by the pi bond and sigma bond is there, and this H0 is applied magnetic field, and there are two fields generated. You can see here paramagnetic field and diamagnetic field, and here the magnetic field and this paramagnetic. The hydrogen atoms appear in the paramagnetic region, and therefore they are deshielded. If the hydrogens appear in the diamagnetic region, in that case they are shielded. I am repeating again. If the hydrogen atoms appear in the paramagnetic region, they are deshielded. If they appear in the diamagnetic region, they are shielded. Okay, this is also not new for you people. This is an anisotropic effect in aromatic compound, aldehyde. In aldehyde also you can see the hydrogen is in the paramagnetic region, so in the downfield region, and the aldehydic protons sometimes appear even at 11 delta value, approximately 11 delta value also. So you can see here. And in case of ethylene, I already told you that the protons are shielded. They appear in the diamagnetic region. This picture, you can see how the hydrogen atoms are lie in the diamagnetic region, and they are shielded protons. We already discussed about the equivalent, non-equivalent. Okay, so far as we have completed three aspects of NMR spectroscopy. Which are they? Number one, number of signals, non-equivalent, equivalent protons. Number two, intensity of the signal. And number three, position of the signal. Under that, we have discussed chemical shift, shielding and deshielding. Let us have some example which are looking complicated, and let us try to solve these, that how the number of signals, how to calculate, how to determine the number of signals. See in this example, this is a CH3 group. Okay, so first signal is for that, A number. Now this is a CH, B type of proton. This hydrogen and this hydrogen have the same surrounding. So third signal for that, and these lower hydrogens have the different surrounding. So fourth signal. Actually, if you not write the structure in this way, suppose the methyl cyclopropane is given to you, then at the first glance it is looking like that. Only three type of protons are there. Which are they? CH3, then this CH, and this CH2 group. These two CH2 groups are looking same. Okay, but when you write the splitted structure of that, you can see here that is the three-dimensional structure. So these protons are different because they have the different magnetic, different chemical environment is there. Same is the case here. Here, see, it is a cyclobutanol molecule. This is OH group. Suppose it is the first signal. Then this is a second signal for this hydrogen atom, which is attached to the same carbon to which the OH is attached. Okay, then see these two hydrogen, this one and this one. Yeah, okay, so these are same, they are having the same environment. So third signal is obtained for that. Okay, this is different because the chemical environment is different. These two protons are also different as they have the different chemical environment. Okay, so in all 6 NMR signals are obtained. So I think this is not new for you people. Just I am refreshing you the knowledge, and then we will move to advanced NMR spectroscopy. Okay. Hope you understand this. Okay, now coming to the fourth aspect of the NMR spectroscopy, that is spin-spin splitting. In actual practice, if you see the spectrum of NMR compound of you can see it from your teachers who are doing the research, or you in your PG dissertation also. Sometimes you have the need, if you are working in the organic chemistry, organic synthesis, there is a need of characterization. So we get such type of spectra, which is shown in the second, this one, such type of spectrum, and not of this type. Okay. So second, that is complicated type spectrum is obtained. Why it is so? It is due to the spin-spin splitting. Now, by considering the very simple example of ethyl chloride, chloroethane, let us see the spin-spin splitting. In CH3, CH2Cl, how many signals you expect? Of course, 2 signals. One for methyl protons and another for methylene proton. And in the low resolution spectrum, you expect the 2 signals. This is for CH2 and this is for CH3. And at the upright position, the signal, very sharp signal of TMS will obtain. But for the compound, we get only two signals, one for CH2 and CH3. Okay. But in the high resolution spectrum, the compound, the spectrum is like this. Same compound spectrum is like this. See, you can see the CH2 signal is split into the 4 lines, which is called quartet. And the CH3 signal is split into 3 lines, that is called as a triplet. Okay, so why this spin splitting takes place? What is the factor which affects, means why this spin splitting is there? What are the reasons responsible for the spin splitting? Let us see. Okay. So the spin of the adjacent proton is responsible for the spin splitting. Splitting occurs only between the nuclei with a different chemical shift. That is very, very important. Splitting doesn't occur between the same nucleus, means having the equivalent. The splitting always occurs between the nuclei with a different chemical shift. That is, in between non-equivalent protons only. Splitting of the signal is due to a coupling interaction. Which interaction is there? Coupling interaction between neighbors, hydrogen neighbors, and is related to the number of possible spin orientation that these neighbor protons can adopt. The spin splitting formula is shown here on the slide. See, you can calculate the spin splitting by using this formula. N plus 1, where N means number of adjacent, non-equivalent adjacent proton, not only adjacent, non-equivalent adjacent proton. Okay, so coming to example, that is CH3, CH2Cl, simple example. Now let us have the look on CH3 signal, how they are splitted first. How many protons are there on the adjacent carbon? 2. You have to count the protons on the adjacent carbon. There are 2, so put the value of N is equal to 2 here in our formula, N plus 1, so we get 3, that is triplet is obtained. Now for CH2 signal, you can see here by using the same formula, how many adjacent hydrogens are there? There are 3 hydrogens. So formula is N plus 1, so 3 plus 1, that is 4, 4 means quartet is obtained. Okay, so it means the number of adjacent protons are responsible for the splitting pattern. Okay, so these are the relative intensities. That is also important. Relative intensities in case of splitted signal, of course. If no proton is there in the adjacent carbon, so there will be no splitting because N value is 0. So 0 plus 1, that is 1, no splitting, singlet is obtained. If value of N is 2, value of N is 1, so 1 plus 1 is 2, this a doublet is obtained. In this way, if value of N is 2, then we get triplet, quartet, 5 lines means quintet, 6 means sextet. And if more complicated splitting is obtained, in that case it is called as a multiplet. And now let's have the talk on the intensities of the peak. These relative intensities of the splitted peaks are of a particular intensity there. You can see here in case of a doublet, both the splitted peaks are of same intensity. So we can say the relative intensity is 1:1. Here it is in case of triplet, it is 1:2:1. You can see the first and the third signal is of same height, but the second signal is approximately double than that of first or third. So it is 1:2:1. In case of 1:3:3:1, yes, got it. Okay, so now how to remember these relative intensities of the peak? What is it? Let us see. See, there is a binomial expansion for that. to calculate the relative intensities coefficient of the binomial expansion, you have to consider, for example, suppose n is equal to 1. Suppose n is equal to 1 means number of hydrogens on the adjacent carbon are 1. Carbon is 1. So our formula is n plus 1. So 1 plus 1, that is 2. So we get doublet. Now, what you have to, that is a binomial expansion is r plus 1 to the power n. Binomial expansion is r plus 1 to the power n. Now, what is the value of n here? 1. So put 1. So after solving bracket, we get r plus 1. What is the coefficient of r? 1. So 1:1 ratio. Now see for the triplet. For the triplet means n value is 2. 2 plus 1 we get 3. Triplet. Put that n value is equal to 2 in our binomial expansion. That is r plus 1 to the power m. Plus square plus 2r plus 1. So the ratio is 1:2:1. For quartet, you can calculate it is 1:3:3:1. But if the n is equal to 6, n is equal to 7, n is equal to 8, at that time it is not possible for us to solve this binomial expansion. If you are very good in mathematics, then you can solve that expression even for n is equal to 99, 100. But if we have not the background of mathematics, then what to do? So don't worry. For that, there is this type of triangle which is called Pascal triangle, which is given by scientist Pascal, which is easy to remember. Of equivalent protons, non-equivalent proton is 1, then we get doublet, and the ratio is 1:1. Triplet 1:2:1, quartet 1:3:3:1, and this is for pentate, sextate, septate. You can calculate it for any number of non-equivalent protons. How to remember it? You know that. Okay. On this because it is already known to you people. So these are the 4 aspects we have discussed. So number 1, equivalent non-equivalent proton. Number 2, intensity of the signal. Number 3, chemical shift, that is position of the signal. And the 5th aspect is you'll see in the upcoming slides. Before that, let us see the solvents which are used in the NMR spectroscopy. All of you know that we required such a solvent in which almost all organic compounds should be soluble, and it's very, very important is that it should be proton free. If it presents that case, the signal of that hydrogen will also appear in your spectrum, and it will be complicated for us. Therefore, we use the non-protonated solvent. Generally, deuterated solvents are used. The commonly used solvents are CDCl3, that is deuterated chloroform, C6D6, that is deuterated benzene. Then you can use carbon tetra proton. Okay, so in this way we can use the solvent, but it should be deuterated. It should be non-proton compound. Okay, and it should be that. Okay, now it's the 5th coupling combination between in the splitted signal. Okay, let us see. In short, I am telling you about this. Yes, suppose this is the splitted signal of a doublet. Yes, I am highlighting this. Yes, it is a doublet. Okay. Actually, doublet means the spacing is not so large. It is a very small space, and it is measured in terms. And that spacing between these two peaks splitted signal is called as a coupling constant. And what is the application, or what is the significance of this coupling constant? It gives us the information about the coupled. For example, take that same example, CH3, CH2Cl. Here CH3 and CH2. Here methyl and methylene are attached to each other. So they have, after splitting, the peaks of both the signals should have the same J value. That is coupling constant. Okay. Now this is for the NMR spectroscopy. You must have the idea about these 5 aspects. Now let us see the new advanced NMR spectroscopy. You have idea, but before that let us see the application that it is used in the MRI, the magnetic resonance image. By NMR spectroscopy we can identify the structural isomers. Here you can see the N-propyl chloride. Yes, it is N-propyl chloride and isopropyl chloride. Both have the same molecular formula. In the first case, we will get the number of 3 signals, and in the second case, we will get 2 signals. So we can differentiate between structural isomer by NMR spectroscopy. Yes, this is the example of cyclohexane, that how it gives the 1 NMR signal at room temperature, but at minus 100 degrees Celsius, there we get 2 NMR signals, because you know that in cyclohexane there are 2 types of protons. 6 are axial protons and 6 are equatorial protons. 6 axial protons form one set of signal and use set of protons and gives one signal. 6 equatorial protons form another set of proton, gives another signal. So 2 signals are obtained, but at very, very, very low temperature. But at room temperature, you know that there is a flipping between axial and equatorial protons, and hence we can't distinguish between the equatorial and axial proton, and in that case we get only one signal. Okay, so now I am moving to the next presentation, which is about the advanced NMR spectroscopy. Yes. Yes, Ashish sir, is it visible?
Yes, sir. Yes, sir, it is visible and audible.
Okay, thank you. Okay, now let's see some further aspects of NMR spectroscopy, advanced aspects, spin decoupling, which is also called as a double resonance. We discuss about this spin splitting. Now spin decoupling. Why the spin splitting takes place? Spin splitting takes place due to the neighborer hydrogen atom, which are non-equivalent. But in case of the macromolecules, such as the proteins, what happens? So many type of set of protons are there, and therefore we get the complicated spectrum. So in case of complex spectra, simplification of spectra is desirable, and the spin decoupling or double resonance provides one such technique. For this, in basic NMR spectrometer, second strong tunable RF source is required. In this single sentence, you can have the idea about the spin decoupling. See, I have highlighted this. The second strong tunable radio frequency source is required to irradiate a particular hydrogen at the desired frequency while scanning the remainder of the spectrum as before. Okay, means 2 radio frequencies are used to cancel the spin, and therefore we get the simple spectrum. Okay. see this example, CH3, CH2OH. So it is the splitted signal, COH. This is singlet, or this CH2, we get quartet. Why? Because on the adjacent there are 3 protons. How many protons? 3. That is our rule, m plus 1. So 3 plus 1, that is 4. Now for this CH3 proton, how many protons are on the adjacent carbon? 2. So 2 plus 1, that is 3. So we get here triplet, m plus 1 rule, triplet. Okay, this is for the simple ethanol molecule. Now here in the second spectrum, you can 2 protons are irradiated strongly with an additional radio frequency at their resonance position. Means 2 RF radio frequencies are there, used there to cancel the spin of CH2. So in this way, the splitting for the CH3 is prohibited here. So we get singlet. Same thing can be done for the CH2 also. In that case, we have to irradiate the CH3 with an additional radio frequency source. Okay, this is just basic idea about the spin decoupling, which is called double resonance. Name itself indicates it, double resonance. Then for the simplification of the complex spectra, we can also use the shift reagent. Generally, lanthanide series, europium is used for the this shift reagent. Provide a useful technique for spreading out PMR absorption patterns, which normally overlaps, without increasing the strength of applied magnetic field. Okay, now let us move to the next point, that is a nuclear Overhauser effect, NOE. See, yes. What is nuclear Hauser effect? Distance between 2 protons should be less than 3.5 angstrom unit. It is given, see, 2 to 4 angstrom unit, but they means in approximate. The distance for the nuclear Overhauser effect, distance between 2 protons should be less than 3.5 angstrom unit. Nuclear Overhauser effect caused by the dipolar interaction between the nuclei. The local field at one nucleus is affected by the local field at another nucleus. See, it is given on the screen. I am repeating again. A spin excited nucleus undergoes spin relaxation via the transfer of its spin energy to that of an adjacent nucleus. The efficiency of this energy transfer is directly related to the distance between the 2 nuclei. The nuclear effect takes advantage of this speed energy transfer, and it is generally 2.8. In a simple experiment of effect, normal NMR spectrum and the integral is determined. If now one irradiated one of the nuclei and record and its integral, the integrals of nuclei closest in space to the irradiation in intensity relative to those nucleus which are removed. Now this nuclear Overhauser effect I will again explain when we touch to the nuclear Overhauser effect. I will again explain when we touch to the our next point, that is Cauchy-Noisy effect. That time it will be clear. At this moment, just remember that for the nuclear Overhauser effect, the distance between the 2 different protons, of course, should be less than or should be in between 2 to 4 angstrom unit. And the nuclear and the one nucleus is affected by the local field to the other nucleus. In that case, nuclear Overhauser effect takes place. We will see again later on. Then coming to the first order spectra and second order spectra. before that, let me again tell you the application of this nuclear Overhauser effect, why there is a need of this. Due to this, you can say the local field of the one nucleus is affected by the presence of another nucleus. The result is a mutual modulation of the resonance frequencies. It is applicable, this Overhauser effect is applicable to distinguish between exo and endo compound. You know the bicyclic compounds, the exo and endo position. Just like in case of cyclohexane, we have axial and equatorial hydrogens. In the bicyclic compound, the terminology is exo and endo. So, to distinguish between exo and endo, we can use this. Similarly, one can use this for the structural and stereoisomers, because the stereoisomer, that is, for example, geometrical isomerism, cis and trans isomerism, it is sometimes difficult to distinguish the spectrum. In that case, the nuclear Overhauser effect is applicable. Now, first order spectra. See this equation. The new chemical shift very, very greater than J value. That is coupling constant. In that case only we get the first order spectra. Chemical shift should be greater than 10 times of the coupling constant for getting the first order spectrum. Chemical shift should be approximately greater, 10 times greater than the coupling constant. Okay, so equation is given here. Delta nu, that is chemical shift, should be very, very greater than J. Chemically, it's now the same coupling constant to every other nucleus. Okay, but I am repeating, chemically equivalent nuclei must have the same coupling, must be constant to every other nucleus. Nuclear pair that fail this test, what is the test? Delta nu should be greater than, very, very greater than J. Approximately 10 times should be greater. Magnetically non-equivalent, and their spectral appearance is in second order. Okay, so I am just saying in one sentence that delta nu should be, that is chemical shift should be greater than J value. In that case, we get the first order spectrum. We will discuss it in detail in the upcoming slides. Then this is about the labeling of the protons. Generally, this is very simple. Inner peaks, the shaded peaks, almost overlap. See, I am repeating again. See, delta nu is very, very greater than J. This type of plate pattern, they are away from each other. If this difference between delta nu by J is becomes smaller, then they are closer. That is AB type of pattern. AB type of pattern. And if in case J, that is coupling constant, is more, in that case, the inner peaks are almost overlap. Okay, again it is same, it is given here. I will skip this. We will move to the next point. Yes. Okay, we will also skip this one. I already told you that the letters A, M, and X are used to designate chemically different protons whose chemical shift values are very different. The term multiplicity is used to indicate the fine structure, that is singlet, doublet, etc. Okay. I will skip this slide. Calculation for line position, I will also skip this. I think you know that. There may be some such type of example asked in the examination that calculate the line position for a triplet at delta 3.2 having J value 7 Hz and the instrument frequency 90 MHz instrument is given. So for calculation of the shift, there is a formula. I am going to skip these slides. Okay, by the way, Ashik sir, what time we have to finish?
Sir, we have 30-40 minutes.
Again, 30 minutes. Yeah. I will correct it. Double bonded compounds. There is a long range coupling. Hence, the adjacent protons as well as the other protons from the molecule also interact and takes part in the splitting pattern. In that case, the car plus compounds, etc. The magnitude of J between vicinal proton means the protons which are attached to the same carbon, like this. The magnitude of J coupling constant between, suppose this is S, and between vicinal proton is influenced by the dihedral angle theta between the vicinal proton. Dihedral angle theta. Okay. The magnitude of J vicinal does depend on overlap and is therefore related to the relative orientation of the coupled nuclei in space. That is the dihedral angle theta. The magnitude of coupling constant, vicinal coupling constant, depends on overlap and is therefore related to the relative orientation of the coupled nuclei in space. That is the dihedral angle theta. See the equation due to car plus, and this gives frequent agreement with the observed values. Equations are given here. You will not see this equation. 10 cos 2 theta, 16 cos 2 theta, it is given. You will be familiar with this graph. This is the graphic representation. See the theta, that is the dihedral angle. Dihedral angle ranges from 0 to 180. You can see here, this is theta, okay? 0, 20, 40, 60, etc. up to 180. And on y-axis, J, that is coupling constant is there, okay? It is a coupling constant. When we plot the graph between coupling constant and theta, what is theta? Theta is the dihedral angle between vicinal protons. See, when there is a dihedral angle 0, see, 0 dihedral angle, J value is high. You know J value coupling constant? It is like 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, generally up to 12. So, at 0, what is the J value? It is higher. At 20, J value is decreased. When the dihedral angle increase, it is again decreased, J value. At 60, you can see, J value is again decreased. See, at 90, it is not to the point, okay, but just imagine. At 90, the J value is the least. Again, it decreases. And at 180, again, you can see here, the J value is nearly 13 hours given. This is the calculus. So, in one sentence, what we can say here, that when you compare the theta, that is dihedral angle of vicinal proton, with the J, that is coupling value, it first term is for 0 and 180 it is more, while at 90 it is less. Okay, this is a calculus curve. The coupling constant reaches maximum when the dihedral angle is 180 degree. We have discussed in the earlier slide that at 180 degree it is maximum. It means when the hydrogens are anti-periplanar with the most effective overlap of the orbital. See here you can see, which I have circled here with the blue ink. You can see on your screen. What is the theta? What is the dihedral angle in between them? It is 1, what is the value? 10 to 13 hertz. However, in this, the two hydrogen atoms, what is the angle in between them? Theta 60 degree. What is the value? J value is 3 to 5 hertz. Okay, so the coupling constant is less when the theta, that is dihedral angle is less, and the coupling constant is more when the dihedral. It is slightly smaller than maximum when the dihedral angle is 0. That is when the vicinal hydrogens are seen coplanar, that is eclipse type of protons, this type of protons. In that case, also the dihedral angle is dihedral angle is 0, but and when it is a minimum when the dihedral angle is 90 degree. That is when the orbitals are orthogonal to each other. Suppose the hydrogen is here, x-axis and y-axis like that, 90 degree angle. In that case, the J value is less, minimum. Okay, so remember, this is related to coupling constant. This curve, that is curve plus curve, it's very important. Okay. Yes. Now see, this is again very important. You know that in case of cyclohexane molecule, when suppose I am I am comparing this OH and this hydrogen, which I have circled. So this OH and hydrogen, these are anti to each other. They are anti-periplenar to each other. Both are at axial position. And what is their position? It is 1, this is second carbon. So if at 1 and 2 position, groups or atoms, they are anti. But if one is axial and other is equatorial, if one is axial and other is equatorial, then it is cis. Okay. At 1, 2 position, I am telling you, if one is axial, this is axial, and this is another axial, they are trans. But if one is axial, and other is equatorial, then it is cis. Okay, so for that it is very important. See what happens here. Just a minute. One of the most important consequences of the Karplus equation is on the order of magnitude of the axial equatorial and equatorial coupling constant in cyclohexane chair conformation. The coupling constant of axial proton is normally large, that is 10 to 13 hertz. Why? Because the theta, that is vicinal, that is the dihedral angle is 180 degree. And we know that 180 degree, the coupling constant is very, very high. Then coupling constant for axial equatorial C, JEE, just a minute. JEE and JEE are in the range of, okay, see here. This is OH, this is hydrogen. Both are, just a minute. Okay, so see here, both are equatorial. Okay, and for equatorial C, it is 2 to 5 hertz because the angle is less. Now here see, one is axial, other is equatorial, the angle is also here less. Therefore, the angle is less, therefore the range of the coupling constant is between 2 to 5 hertz. Okay, so this is all about the Karplus relationship. See here, again one example is given. In the first example, HAHB, they are on the same side, so it is cis. In the second, HAHB, they are trans, and as they are trans, 180 degree apart from each other, the J value is more, that is in between 11 to, means more than 11, while in case of cis, the J value is less. Okay. Okay, I am not going to detail about this now. Examples are given here. This is again about the cyclic compounds. I am going to skip this slide. Okay, it is a very vast topic. Okay, now let us come to the next point. We will see noise and heteronuclear correlations, that is hector spectrum in short. The most important two-dimensional NMR experiments for solving structural problems, that is COSI, correlation spectroscopy, noise, that is nuclear Overhauser enhancement spectroscopy. Most modern high-field NMR spectrometers have the capability nowadays to acquire this COSI, noisy, or heteronuclear shift correlation spectroscopy, that is HSC. We will see in short about this spectroscopic technique. Don't afraid about these names. In very short, I will brief you about this spectroscopic technique. 2 NMR of one compound. COSI spectrum means 2 NMR of one compound. COSI takes advantage of the fact that the coupled signals have equal J values. We know that. Taking the same example, CH3, CH2, Cl. CH3 and CH2 are coupled to each other. So the coupling constant between these being the same. To the next page. I will show. COSI takes means to consider the fact that the coupled signals have equal J values, that is coupling constant. You can see here off diagonal peaks. See, this is the diagonal line. This is the diagonal line. The points which are on diagonal line, leave that point and see the other points which are, these are shown. That is off diagonal lines. These points are peaks, that is cross peaks in COSI spectrum, points to heterogens that couple with each other. Remember that correlated points should not be on diagonal line. See, this point and this is the same spectrum. Same. These 2 points to it means this proton is highlighted and this proton, these 2 are same. So this and this are same. Here. Now,
Sir, you are not audible, sir. I think due to some network issues, Pradeep Tekade sir is not available.
yes, please. Am I audible now?
Yes, sir. Yeah.
Okay. Just a minute. Within 5 minutes, I will complete. Okay.
Okay.
Okay, am I audible now?
Yes, sir.
Yes, sir, you are.
Okay. Okay, so what I want to convince you that what is the difference between quasi and noisy. Noisy shows through the space interaction within the molecule. Means, for example, two methyl groups are there which are in the same vicinity. In that case, that interaction, space interaction without bonding. See, quasi consider the bonding interaction, means bond sigma or pi bond, while noisy consider the we can say it is a van der Waals interaction or what type of interaction that the two groups, for example, methyl groups are there in the close vicinity of each other. In that case, noise is applicable. And finally, I will skip this and I will skip this proton exchange reaction. I think it is known to you. Just a minute. This is about the heteronuclear correlation spectroscopy. Head-core spectroscopy tells us about which hydrogens are connected to which carbon. Cross peaks in head-core spectrum allow us to easily correlate 1H hydrogen, means 1H PMR, 1H NMR with the 13C NMR. Just like a quasi, in quasi, two spectrums of PMR spectrum are taken, that is 1H spectrum. While in head-core, that is heteronuclear correlation spectroscopy, one is of C13 PMR.